Hello everyone and welcome to Cycle 1 Solubilization of Mefenamic Acid Experiment Pre-Lab Information. The objective of this cycle is to evaluate various approaches to solubilize a weakly acidic drug. We will be using mefenamic acid as a model drug. And here we will evaluate three different approaches. First, pH solubility profile. The solubility will be studied in different buffer systems. For this purpose, 6 different buffers with different pH values will be prepared, and the drug solubility will be determined in these different buffers at constant temperature and pressure. The second approach is the effect of co-solvent. And here, the solubility at constant pH and temperature and variable concentration of co-solvent, ethanol as an example, will be evaluated. And the third approach will be salt formation. For this purpose, sodium salt of mefenamic acid will be prepared and checked for solubility, aqueous solubility improvement. What things you need to know? Theoretical information before starting this cycle. First, as a qualitative term, solubility is defined as the spontaneous interaction of two or more substances to form a homogeneous molecular dispersion. While, as a quantitative term, solubility is defined as the concentration of solute in a saturated solution at certain temperature. As you know, solutions are either saturated, undersaturated or subsaturated, or supersaturated. At saturation, the rate of salting in is equal to the rate of salting out, where we have a constant concentration. Generally speaking, solubility is affected by physical factors like temperature, pH, and pressure. Pressure specifically affects the solubility of gases, and physicochemical properties or chemical and physical properties of the solute as well as the solvents, such as melting point. Remember that solubility is a function of chemical structure. Salts of acids and bases having the best chance of attaining the desired degree of the water solubility at the desired pH, while other compound classes, either neutral molecules or very weak acids and bases, which cannot be solubilized in water within the desired pH range, may require the use of non-aqueous solvents. Examples on non-aqueous solvents that can be used in the parenteral product are listed in Table 5 in the assignment chapter. Factors affecting solubility of solids in liquids include temperature, molecular structure of the solute, nature of the solvent, presence of co-solvents, also crystal characteristics, polymorphism and solvation, particle size of the solid, pH, common ion effect, effect of indifferent electrolytes on the solubility product, effect of non-electrolyte on the solubility of electrolytes, effect of electrolytes on the solubility of non-electrolytes, complex formation, and solubilizing agents, the presence of solubilizing agents. This figure shows the effect of temperature on the solubility of different compounds. And this effect depends on the fact that solubilization process can be considered as chemical reaction. These chemical reactions may be endothermic, exothermic, or a combination of both. Also, some solubilities are unaffected by temperature. Notice the examples on the figure. For more information, my recommended read is Chapter 2, Dissolution and Solubility from Pharmaceutics, The Science of Dosage Form Design by Alton, your textbook. This chapter is attached as a supplementary read. As we mentioned, pH is one of the factors that may affect the solubility, and we are concerned about the effect of pH on weak acids, mefenamic acid as an example, in these practical sessions. This effect is studied as pH solubility profile. A pH solubility profile is plotted or constructed as solubility using any suitable solubility expression versus pH, using the correct pH range for each studied material or drug. This range should be equal to pKa plus minus 3 to 4 units, and will be entitled as pH solubility profile for this studied molecule or drug. And please mention here the conditions on which we are studying the solubility, for example, at certain temperature and pressure. Drugs are either weak acids, have functionalities like carboxylic acid, imide, sulfonamide, phosphate groups. Examples on these weak acids are mefenamic acid, salicylic acid, and ibuprofen. Drugs may also be weak bases and have functionalities like amine group. Tetracycline is an example on this class. Other classes include neutral molecules. Paracetamol is an example on this class. Drugs may also be amphoteric in nature, containing both acidic and basic groups or functionalities. Ciprofloxacin is classified as amphoteric molecule. Here how would pH solubility profile of weak acids, weak bases, neutral compounds, and amphoteric compounds would appear. For this cycle, you will have an assignment chapter. This chapter has been uploaded to your e-learning page under this topic. Notice that the required information are those highlighted with yellow. As I said in the beginning, we will need to prepare buffer solutions. Buffer solutions are solutions that resist pH changes upon the addition of small increments of strong acids and strong bases, and these buffers are prepared using weak acids with their conjugate bases or weak bases with their conjugate acids. Buffer capacity is a quantitative measure of the resistance of a buffer solution to pH changes upon the addition of small increments of strong acids or strong bases. It is worth mentioning that our blood is a buffer solution, and the buffering agent in our blood is the bicarbonate. One of the most important buffering agents and one of the most widely used buffering agent is phosphate. Why? Because it is considered polyprotic. What does that supposed to mean? It means that it has 3 protons, H3PO4, available to be donated, and this allows it to cover a wide pH range. The ionic strength of a solution is a measure of the concentration of ions in the solution. Ionic compounds, when dissolved in water, dissociate into ions. The total electrolyte concentration in solution will affect important properties such as the dissociation or the solubility of different salts. One of the main characteristics of a solution with dissolved ions is the ionic strength. The ionic strength, I, of a solution is a function of the concentration of all ions present in that solution and calculated as I, the ionic strength, is equal to the half of the summation of all ions concentrations, molar concentrations, multiplied by the squared value of this ion charge. Here is an example on how to calculate the ionic strength of a mixture containing 0.05 molar Na2SO4 and 0.02 molar KCl. Remember that ionic strength is one of the factors that affect the buffering capacity. More information about buffers and how to prepare buffers, the two methods, are available in your student manual. Also, one of the objectives is to study the effect of co-solvents on the solubility of weak acids, or as a method to enhance the solubility. Co-solvents are defined as water-miscible organic solvents that are used in liquid formulations to increase the solubility of poorly water-soluble substances or to enhance the chemical stability of a drug. Co-solvency then refers to the technique of using co-solvents for the stated purposes. It is also commonly referred to as solvent blending. Co-solvency has been used as an approach for preparing liquid drug preparations throughout history of drug formulation. Certain drugs of botanic origin known to be poorly soluble in water and required formulation in water-ethanol mixtures in order to deliver an adequate dose of a drug in a small volume of preparation. A common example of a class of formulation containing co-solvents is the elixir, which by definition is a sweetened hydroalcoholic solution intended for oral use. Tinctures, which generally contain even higher amounts of alcohols than elixir, are another classic example of a liquid dosage form containing a co-solvent. The need to employ co-solvents in the formulation of new drugs as solutions for oral, parenteral, and topical use remains high, especially with the increasing structural complexity of new therapeutic agents. In many cases, co-solvency can increase the solubility of non-polar drug up to several orders of magnitude above the aqueous solubility. This would be significant, for example, in a formulation problem where it might be necessary to increase the solubility of a drug 500-fold or more. The use of co-solvents to prepare solution of non-polar drugs is a simple and potentially effective way to achieve high concentration of drug. The primary disadvantages of co-solvency include the potential for biological effects and the potential for drugs that have been solubilized using co-solvents to precipitate upon dilution with aqueous fluids. The biological effects of a co-solvent that may limit or eliminate its use in drug formulations include their general toxicity, target organ toxicity, tissue irritation, or tonicity with respect to the biological membrane. In addition, precipitation of a drug upon dilution with aqueous media or during injection or application to mucous membranes must always be considered in deciding if a co-solvent can be used as a vehicle for poorly water-soluble drugs or not. Other considerations include the viscosity, tonicity, and taste, as well as the effect of co-solvents on the solubility and stability of formulation components other than a drug. When used as a method for increasing the chemical stability of a drug, co-solvents may be effective by one or two mechanisms. If a drug is susceptible to hydrolytic degradation, co-solvents may reduce the degradation of the drug by substituting for some or all of the water in the formulation. Alternatively, a co-solvent may enhance the stability of a drug by providing a less suitable environment for the transition state of reactants, provided that the transition state is more polar than the reactants themselves. Probably, salt formation is the most widespread and efficient method of increasing solubility and dissolution rates of acidic and basic drugs. Whether certain acidic or basic drugs would form salts, and if salts are formed, how easily they would dissociate back into their free acid or base forms depend on interrelationships of several factors, such as intrinsic solubility, pH, pKa, Ksp, the solubility product, and pH max, pH of maximum solubility. Here are some questions for you to answer. During a practical session, we will discuss the calculations required to prepare buffer solutions. Then you will need to do the pre-lab calculations required in the beginning of the procedure and the reports required data in your portfolio reports. Thank you.